All right, so here I am with the amazing Dr. Tyler Bradshaw, who's a faculty member at the Department of Radiology, University of Wisconsin. And we recently had the pleasure of working together on this really beautiful work that he led and was recently published in Radiology AI. And I thought it would be very good for us to have a conversation about it because there's a lot of nuances. There's a lot of really very interesting things going on here. So thank you very much, Tyler, for being here.
Yeah, I'm happy to be here. Thank you, Armand, for inviting me, and I'm happy to talk about this work that we put together.
Thank you, thank you. And so perhaps you could give us a bit of a backstory of what happened. How did this paper come about?
Yeah, happy to. It's kind of interesting because it started off as part of the SNMMI AI task force. We were putting together recommendations on how people should conduct machine learning studies. And part of that was cross-validation, where we were given recommendations on how to do cross-validations. And so when I was writing that section, I was doing a lot of reading, trying to figure out, what is the best way? How do you handle different scenarios? And the literature was kind of confusing. I found a lot of people just went to blogs, right? There were blogs that people would follow. And sometimes those blogs would contradict each other and you never knew, how valid they were. So I just did a lot of deep dives, and then we put that paper out and recommended some cross-validation techniques. Yeah, the AI Task Force recommendations paper, we put that out. And I remember I got several questions from colleagues and other people. I think the number one thing people asked me about was cross-validation. They had questions about how to do it. And so that led to more deep dives into the literature, into blogs, into kind of some packages, Python packages, trying to figure out how to do this. And working with you, we kind of put this together as a guide for other people who are in that same scenario.
Yeah, I mean, I remember those sort of months we were struggling with this, that I was having heated meetings myself within even our own lab, and people are saying, well, no, you got to do it this way, you got to do it that way. And there's many different ways people do cross-validation, right? And so when this came about, we were struggling, and I think writing this paper sort of brought a better sense of understanding of how things are done and perhaps how things should be done.
Right. I agree. I don't know if we have, a scenario, a cross-validation technique for every scenario, but I think we definitely put forth better kind of capture the field and what are best practices in general.
Cool. So if you could please just take us through the motivation behind this further, and let's see what we came up with.
Yeah, so I think it's important to recognize, it's important to kind of get this idea of what you're trying to do with cross-validation, but more importantly, what are you trying to do with machine learning? Because machine learning is all about making predictions on new data. So often in research, we think about, I got to publish how my algorithm does on my data. But the whole goal of any machine learning algorithm is to apply it to new data at some point. So when you're doing machine learning, when you're doing cross-validation, have the mindset of, I want to know how it's going to do on new data, not just my data, but new data. And so that's called the generalization error. And that's what you're trying to measure. And so one problem with machine learning is that it's prone to overfitting. Right. And I think we all intuitively know this. You can get overfit. Your model can get overfit on your training data. And that's the reason you can't use your training data to measure the generalization error, because you're going to get over optimistic results, meaning you're going to think you get 100% accuracy, but when you go to apply it somewhere else, you might be at 50% accuracy. So you can't use your own training data set. You have to use something else. And that's where cross-validation comes in.
Yep. It's of course in the early days, people were even publishing papers without doing that, further validation, right? And of course, people were showing extremely good results, and reviewers were even they didn't have the tools and the equipment to even understand some of these subtleties. But of course, now we're in a different world. People at least have somewhat of a better understanding of these issues.
I think that's absolutely true. I think, yeah, people weren't using any sort of kind of cross-validation method previously, and in some instances, I think computer science has used this for a
Yeah,
long time. But I think even now we still have problems, and I'm going to get to that, why
yeah,
we still have problems even using some of these methods.
yep,
So this slide just shows that, this is the typical way people think about training machine learning models, is that you split your data, do a one-time split where you say, let me take 60% of my data for training, maybe 20% for validation, and then 20% for testing. And just to clarify, the validation is what you use, that set is what you use to fine-tune your model's hyperparameters, or to select an algorithm. If you're considering multiple algorithms, you use that validation set to tell you which hyperparameters or algorithm is the best, and then you apply it to your test set to measure the generalization error.
yep.
So this is the bread and butter, right? People have been doing this for a long time. Problem is, this doesn't work well with small data sets. And small is a very relative term. I don't have a definition for small,
Yeah.
but when you get to small data sets, this starts presenting some problems.
And that commonly is the case in many studies in medical imaging. We don't have massive data sets. Yeah.
Exactly. So what are the pitfalls? I'm going to talk about two of them with using just this one-time split method and how we can solve it with cross-validation. One is non-representative test sets. And then the second pitfall is tuning to the test set. And both of these are problematic, and both of these happen now in literature. So non-representative test set, this simply means that your test set that you split out doesn't actually represent the data or the population that you want to apply your model to. And so when that test set doesn't well represent how you want to use your model, it can give you wrong predictions or wrong generalization error, right? You can be over optimistic and think you're going to do excellent. And we see this all the time, that when you actually apply it to the data, it doesn't do well. So why does this happen? Why can you have test sets that are not representative? One problem is, it's not a well-known problem, but I've seen it talked about quite a bit in certain circles, is hidden subclasses. And what do I mean by that? Hidden subclasses are groupings within your data set that you don't know about.
Yep.
A good example that I think is relevant, well, it was relevant a few years ago, was with vaccines with FDG data sets. So you can imagine some patients were getting vaccinated. I mean, a lot of patients were getting vaccinated recently, and they're going to get FDG scans, and that can elevate some of the lymph nodes, right? And those aren't patients you know about. You don't know who that group of patients are, but an AI algorithm trying to interpret disease or trying to predict where disease is may struggle with that grouping of patients. And there could be lots of different subclasses that you just don't know about, right? Patients who only have disease in a certain area might be subclasses. Patients who have very small lesions might be a subclass.
So in the middle plot you're having there, on the x-axis, you have different kinds of classes, representing various diversities that might exist.
Exactly.
Some could be easy to sort of deal with.
Yep.
And some are much more difficult and confounding or complicated situations. Yeah.
Exactly. Some patients model might do perfect on because they're very easy, a subclass. Yeah. Some patients, some groups might be very difficult for your model. So if you just do a one-time split and your data set is small, then what might happen is you might oversample in your test set, just randomly oversample the easy cases. Yep. And have fewer hard cases, or vice versa. Either can happen. The problem with one-time splits is you don't know where you are along that spectrum. Because these are hidden subclasses, there's no way to handle it. You just don't know. So you might get very optimistic results because your test set just happens to be easy.
So the bottom right figure, you have an example where easy cases are oversampled. And yep. So if you're training on those oversample easy cases, suddenly you show up and you do your testing and you have more difficult cases there, suddenly your performance would go down, correct?
Right. If your test set has more difficult cases, then you're going to your model's not going to do as well.
And in a typical single split, you could get unlucky or lucky depending on how you do it, right?
Exactly. And so imagine if somebody wanted to kind of optimize this, right? And kind of not quite p-hacking, but kind of hack this to get the best test set generalization error, right? You can imagine you could do really well with a certain split.
Put the easy cases in the test, or just
Exactly. And that may not be intentional. They just
it may not be intentional. Yeah.
Pick the seed, the random seed that gives them the right result. So this is a problem. As you can imagine, this goes away once the data set is large enough, right? Once it's large enough, then this problem goes away. But it is a problem with small data sets.
Because when it's larger data set, it's going to be very unlikely that you're going to get these kind of asymmetric, distributions, right?
Exactly. That's right. So this is one reason one-time splits is not good.
Yeah.
The other reason, the other reason why you can have non-representative test sets is that your data set, or you can have what's called data set shift. And this is simply where you train and test your model on one type of data, distribution of data. And then when you go to use it or apply it, you meet a different distribution, and that has different characteristics. We see this all the time in literature. It just may not work. So those are non-represented test sets, which cause problems. Pitfall number 2, I think this one is more prevalent in the field, and people don't really talk about it a lot, but I think it's very interesting. And it's tuning to the test set. So what that means is that you've accidentally, hopefully you're not trying to, but you've accidentally tuned your models, and I mean the hyperparameters, the parameters, you've tuned it in a way to your test set. Even though your test set is held out and you're not directly training the model on it, your model is tuned to the distribution of data in that test set. And I have a good example of this. And this is, you can see this table here.
Yep.
This is a blog post from a guy named Greg Park. And he was a Kaggler. So Kaggle holds these challenges, and he participated in one of these challenges, and he was doing awesome. So this table shows what's called the public leaderboard. And this is a test set that Kaggle holds out. It's the test set, but you can submit as many models as you want to see how your model does on that public test set. And you can see how you rank compared to the others. And so Greg Park here, he submitted 42 different models, and he kept climbing up that leaderboard, and he got second place in the public leaderboard. Now, what happens with Kaggle is at the very end, you move to a private leaderboard or a private test set, and you can only submit one model. You can only submit one solution, and you see where you land.
So this performance, Tyler, that is very top performance, is it one amongst those 42 entries, or is it the collective?
Yes, it's one of those 42.
Yeah,
exactly.
Yeah, and then he this model of his is being taken to the holdout test set number 2, which he hasn't seen, of course.
He hasn't seen, and you don't get to keep submitting models. You get
and he's all
shot.
expecting this is all going to be also great, and then what happens?
Yeah, right. He's going to make the money. He's going to win the prize.
Yeah.
But what happened is poor Greg Park dropped down to 52, number 52. And not only was he 52, he said that he placed even below the benchmark solution that the organizers provided. so just the basic model that he did worse than.
Yeah.
And but kudos to Greg, because he kind of dug into this, tried to figure out what was going on. And so this is a plot here of different participants in the Kaggle challenge and how many models they submitted on the x-axis, and the y-axis is what was their rank. How well did they do?
Yeah.
And what we found was that the people who submitted the most number of models did the best on the public leaderboard. There's a clear correlation there.
Because you pick their best model amongst those many models that you're submitting. So
exactly.
Yeah.
So what's happening is you're getting a model that happens to have the right parameters, hyperparameters, the right algorithm, configuration, whatever it is, and it's randomly, and I think this is important to understand, it's randomly well matched to the data in the test distribution. And so you just happen to have a good match, and it's totally random, but if you do enough submissions, you're going to get a good match. Now, what happens when you go to the private leaderboard where you can't submit many models?
Yeah.
This is the correlation. So the number of submissions was the number of submissions on the public leaderboard on the x-axis. And then the private leaderboard rank, you can see there's no correlation. So meaning those people who were doing 60 models on the public leaderboard, it didn't give them any advantage. In fact, it just confused them. It just gave them optimism that they shouldn't have had.
Yeah.
And so this is the problem, is that you can tune your model to the test set on accident just by retraining your model a number of times.
Yeah. And so this is, to me, this is very meaningful because, of course, you know, hopefully nobody does training only. People are, of course, doing some kind of validation, but it is possible that if you're throwing God knows how many models at your data, one of those models is just gonna work out nicely in the validation, and you're gonna think, well, this is amazing, but it may not be amazing. It may have gotten lucky in the validation because you're throwing too many things at it, right?
Exactly. And then here's the question, Armand, is if you're developing a new model, and think about how many different configurations or attempts would you put into making a new model versus how many times would you train a benchmark or a reference model, a comparison model that you're trying to compare against, right? Almost everyone will train that comparison model once.
Exactly.
Just one time, and they'll train their own model 20 times, 30 times, right? And it's not a fair, so it becomes not a fair comparison. And that's why you should only use your test set once, ideally. It's very much an ideal because it's
an ideal, and of course we'll talk about it because in practice there's issues with that, right?
Right. Yeah, it's an ideal, right? But the problem is if you just keep testing your model, you're going to get over optimistic results. This diagram here essentially just represents what we talked about. The idea that if you train n models, those models are going to have a distribution of performance. Yeah. And if you just pick the best model, let's say, so the model performance is the x-axis here. If you just predict like one of the better models and then go and apply it to your external test set, it's going to fall somewhere in this distribution. And this is where you get a performance gap. This is where you have your internal test set says 90%. You go and apply it to an external test set and you're down at 70%, right? That's your performance gap. And one of the causes of that is this training too many models.
Yep. So
it's interesting to also think about, just to, for people to think about, is in this private leaderboard for Kaggle, right? Let's say 1,000 people submitted models, and in the best model was this one.
Yeah.
But do you think that's really the best one? Because 1,000 people submitted models, and these are the rankings of those 1,000 models. And so if you took that model and applied it to the whole population, that model is probably overfit to the private test set.
Yeah,
by virtue of so many people submitting models. So anyways, it's something to think about, has implications for data science competitions, but also for how we treat kind of research and development.
Absolutely.
This plot is from a paper that came out in Radiology AI that just shows that about 80-90% of models that get externally validated, 80-90% of those models have a performance drop when they go for external validation. So this is a prevalent problem. It's happening everywhere, and you should expect it. You should just expect a performance drop.
So yeah, so what can we do to minimize or reduce this effect?
Yeah, well, let's talk about cross-validation.
Yeah.
Good segue. So cross-validation is one way that you can, I mean, the goal is really to not trick yourself into thinking your model's doing better than it is. You don't want to trick yourself, and certainly don't want to trick the public, when you're publishing your papers. So cross-validation can help you do this. And so why would you do cross-validation? I'd say there's 3 reasons you use cross-validation. The most important being measuring the generalization error without over-optimism. The other 2 would be selecting an algorithm or tuning hyperparameters. And you can use cross-validation for that. So we're going to talk about different techniques for cross-validation. There are several techniques. I'm only going to cover a few of them. There's all these different variations of them, and each of them have pros and cons. Each of them are appropriate to use in certain scenarios, but maybe inappropriate to use in others. So we're going to dive into that.
Yeah.
I do have a note here that I added in. It's important to know, and I'll explain this as we go, that when you're doing cross-validation, unlike when you do a one-time split, you're not testing a single model to see how that model does. You're testing your development pipeline to see how well your models built using your pipeline, your methods, how well they do.
I think that's a very good one. Yeah, I mean, we'll discuss it, I think, but it was a deep, almost philosophical discussion we were having.
Yes.
Is that we're not testing a single model, but we're testing the way a model is derived, and that's what we're validating. But I think we'll discuss this more, because this was a very sort of an illuminating back and forth that we were having back then. Yeah.
You kind of have to shift the way you're thinking about
kind
of model evaluation, is to think about pipelines rather than single models.
So let's talk about this more in a bit. Yeah, for sure. Okay.
So here are the ones we can talk about. Just in order, I'll read them. You have a one-time split, which we've already talked about.
Yep.
K-fold cross-validation. And there, I talk about two variants here: a folded test set and then a holdout test set. And those are different. Leave one out cross-validation, nested cross-validation, select shuffle test, random sampling, bootstrap, and then the last one, leave one institution out, which is very much just leave one out cross-validation, but on an institutional level, on a central level.
And of course, these are elaborated in the paper, but I think we'll talk more about them.
Yeah, we can talk about some of these. So we've already done this one-time split. We've talked about it. I'll just say the pros and cons to each of these. The pros is this is very easy to implement, and it is actually very accurate if you have a big data set. The cons is you can easily tune to the test set on accident or intentionally. It can be non-representative test sets for small data sets. Plus, you only get a point estimate of your performance metric. You don't get confidence intervals, which is a con. It's not a huge deal, but it is. Some of the other methods do give you confidence intervals. So now we'll move on to K-fold cross-validation. This is K-fold with a folded test set. And what you do in K-fold cross-validation is you take your whole data set, that's this gray bar on the top, and then you split it into groups, into folds. And so we're here, what I'm showing is called 5-fold cross-validation.
Yep.
And I've split the data set into 5. And then what you do is you have these sessions. For 5-fold cross-validation, you have 5 sessions. And each one of these, you take one of the folds and you hold it out, and that's your test set for that fold, for that session. And then the remaining 4 are your training set. And so you train your model, and then you get your model then gets applied to this held out test set, and you get a number that's your performance metric. And you store that. Then you go to session 2 and you pick a different fold to be your test set.
Yep.
And you do the same thing. And so in the end, you do this for all 5, and you have 5 numbers, right? 5, whatever, accuracy, dice scores, whatever they are. And then you take the average of those, and you can take the standard deviation to get confidence intervals of how your model is going to perform. And this is K-fold cross-validation.
And that thing at the bottom that you have for the final, can you elaborate that?
Yeah, and this is a principle that I think it's lost on a lot of people, is that, you know, the reason we develop AI models is so we can deploy them at some point.
Exactly.
And so a lot of people do this K-fold cross-validation, and then they don't know, well, I've trained 5 models here. Yeah. You know, there's 5 different models. Which one do I use?
Yeah, so basically, you're doing these 5 different folds, and in each of those folds, in each of these efforts, you're ending up with 5 different models, because the weights in the training are now different, because you did it 5 times. So you're going to end up with 5 different models. So which one are you going to report, and which one are you going to share with others to test? Exactly.
That's the problem. And the answer is that you don't use any of those 5 different models you have. You're not going to use any of them. What you do is you pull all the data together again, and you train on the full data set. And again, I don't think people appreciate this, but that's the best way to get your model, because that model should then be at least as good as what you measured using this cross-validation technique. So you can think of it as cross-validation technique is just giving you, it's a method of measuring how good this final model is going to do when you go to apply it to an external set.
Yeah, exactly. It gives you a sense of how generalizable it is, but at the end of the day, you have to come up with a model to share it. And so this is the way we're recommending people do it. Yeah.
Exactly.
Okay. And so what are the, I guess you have here some pros and cons. So can we go over those?
Exactly. Yeah. The pros of this method is all samples are tested once, which is nice. There's a low bias. And what bias means is if your number that you get out from this is, say, 90% accuracy, then when you go to apply it to an external test set, it should be about the same. It's a low bias. And so K-fold has a low bias. There's no tuning to the test set. And, when we talked about a holdout test set, you can tune to it because you can keep training different models. Problem with K-fold or I guess the advantage of K-fold cross-validation is that the test fold is changing with every session. And so you can't tune to that test set. And so it fixes that problem. The other nice thing is that you get confidence intervals, because you get 5 measurements, and those are your, the standard deviation is your confidence intervals. The cons to this approach is that there's no validation set.
Yep.
So there's no validation set, which means you cannot tune your hyperparameters.
Yeah.
Right?
Yeah.
So let's say you have a UNet and you want to know how many epochs to train it for. Typically, you would have a validation set that you would measure how many if you're doing 50 or 100 epochs, which one's best. You'd have a validation set, and then once you figure out what's best, you apply it to the test set. With this variant of K-fold cross-validation, you cannot tune your hyperparameters. So you can only use it for your model.
So in a way, in that philosophy that we're testing a pipeline, this particular pipeline does not involve hyperparameter tuning, and therefore you kind of ultimately showing the generalizability and performance of a pipeline that doesn't do hyperparameter.
That's a good way to put it. That's a good way to put it. Yeah, I like that.
Yeah.
Yeah. So again, you wouldn't use this method if you want hyperparameters tuned, or you want to compare algorithms for algorithm selection.
Yeah, and we'll discuss that more. But when you're
we'll tell you a method that you can use. So here, the next one is a method that you can use if you want to tune your hyperparameters. Right. This is K-fold cross-validation with a holdout test set. And I'd say this is probably one of the more commonly used K-fold cross-validation methods in general. And the way this works is you have all your data, and right at the start, you split off your test set. It's a one-time split. And then through this K-fold with the rest of the data, you go through this K-fold cross-validation pipeline, and you use validation sets. These ones that you hold out here are validation sets and not test sets. And this allows you to select your algorithm. So you may want to compare different algorithms. You may want to tune your hyperparameters. You may want your UNet to have depth of 3, 4, 5, whatever it is. You compare all of those by training each of those models with every session. So one session you might train 5 models, and you train on the training set and then evaluate it on the validation set. And you do that 5 times here. This is 5-fold cross-validation. And the end goal here is to figure out which algorithm is the best, which set of hyperparameters, or which, essentially which set of hyperparameters is the best. And you pick that one. When you pick that final one, you train it on the training data and test it on this test data. So this is using a holdout test set.
So that allows you to.
Yeah, go ahead.
This allows you to compare multiple algorithms or different hyperparameters, and ultimately see what its performance is. Though you won't be able to put an error bar on the test.
I'm not a big fan of this approach because you still have all the problems associated with one-time splits, right? So the nice thing is that this is going to be accurate for large data sets. Yeah. And you do have a validation data set, but the cons are that you can still tune to that test set. Yeah. You can, if you do this workflow many times, you might end up just tuning to that one-time test set.
sorry, I mean, there's this sense, there's this red line that sometimes people talk about. It's like, I want to put this test set aside. I don't want to have anything to do with it. And then somehow people feel that if you sort of permute, do a permutation of the test, which we'll talk about later, it's almost like you're breaking some kind of a rule. So
yeah.
how do you take that?
Yeah, I mean, it's an interesting idea. I think if you kind of were raised on the one-time splits, that's kind of what your intuition is
yeah.
If I put off the test set, you don't touch it, you don't manipulate it. But with cross-validation, you do keep manipulating the test set, right? But you just use it, you do it according to some systematic algorithm.
Yeah.
So that you're not overfitting to it.
Yeah, I think again, if the data set is massive, this makes perfect sense, because that test set is supposed to be representative, and the training is supposed to be representative, right? But if it's not absolutely massive, or massive, whatever that means, then we run into the same problems, right? So we're kind of recommending that mindset of doing the test only once may not be the best for typical data sets, right?
Exactly. And I think we can provide some recommendations at the end. And in the paper, we go through that, what's recommended in which scenarios.
And now again, here in the very last step, where the whole thing is brought in, and there's another training, like, is that necessary, or why is that done? Why can't we just take the selected model in the last one, just use that and say, here's a performance?
Yeah, it's a good question. I mean, it's the same principle as last time, is use that training data, because you want your model to be at least as good as what you measured using cross-validation. And so if you pull all the data for the final training, you're going to have just a better use of your data.
So in an interesting way, you're at this final stage, and you've selected the model, you've selected the way you do this, and you've of course done a testing on it, and you can report how good it is. You might as well now do the final thing and use that extra data to retrain, because that's going to be as good, and you've already verified the way you do it, the pipeline. So there's nothing wrong with this. There's nothing wrong with actually using that extra data that you used as a test originally, and bring that in and do a final training, and that's the model you're going to share with everyone, right?
Exactly. And the hyperparameters you're going to use, because those are the best ones from this algorithm selection step that you use to cross-validation.
Yeah.
So.
All right, but again, you're not a huge fan of this. Yeah, you're not a huge fan of this. Yeah, if you have limited data or moderate data sizes.
Yeah, I think if you have big enough data to do this, you can just do a one-time split.
Yeah.
All right, so now we're to the beast, the nested cross-validation.
Yes.
This one's hard. This one's hard to explain. At a high level, I'm showing it at a high level here. What you do, this is how you do hyperparameter tuning within k-fold cross-validation without having to hold out test set. Yep. So if you have a small data set and you need to tune some parameters or compare algorithms, nested cross-validation is an option. And what it is you do the same thing as before. You split your data. What I'm showing here is 5-fold cross-validation, the outer loop, because there's an outer loop and an inner loop. Yep. In this case, there's a 5-fold cross-validation in the outer loop, 4-fold cross-validation on the inner loop. And what happens on the outer loop? You do testing, but on the inner loop, you do algorithm selection. And so for each outer loop, for every time you do an outer loop, so a session of the outer loop, you're doing the inner loop, the full inner loop, to select your algorithm, and then you're testing it in the outer loop. I'm going to go through this in detail. So I know it's a bit vague right now, but that's the kind of
Again, selection could be when you're testing multiple different algorithms, or picking the hyperparameters for a particular.
I like to think that hyperparameter tuning is just algorithm selection by a different name. Yeah. Because you can think of 10 epochs, 20 epochs, 40, 50. Those are all just different algorithms, right?
Okay. Yep.
So the nice thing about this is it's accurate. It's kind of the gold standard, maybe, cross-validation. I'll go out on a limb and say it's the gold standard. It has a validation set, and all the samples are tested once. The cons are that it's computationally demanding, because you have to do, in this case, 5 times 20, or sorry, 5 times 4, so 20 sessions. And if you have 10 models you're comparing, that's 20 times 10, right? So it becomes computationally demanding. And it can be difficult to interpret. I said difficult to implement. It's actually not that difficult to implement because there's some convenient code for doing that. In fact, here's the code on the right here. This is using sklearn, a package in Python, where they really, made it. I mean, you have 5 lines of code here. There's a lot going on in each of those lines. There's a whole package built around it. But this is really how you do it. Now, don't be deceived though, is that even though it's simple to code, it's a little hard to understand and comprehend. So I'm going to go through this on the left, step by step, and kind of discuss what's happening with nested cross-validation. But one thing I want to emphasize, we've said it a few times, but you really need to think of it, think of this principle when you're looking at nested cross-validation. And that is that you are testing a pipeline. You're not testing a model, you're testing a pipeline. And you'll see what I mean when I go through this. So let's go through the first step. I showed you a 5x4 nested cross-validation before. I'm going to move to a 3x3. 3 outer, 3 inner, because it's easier to explain and show. So first step is that you do a cross-validation step where you split your data into 3 groups, and you're going to do 3 what's called outer sessions here. So you have a test. One of the folds is your test set, and then the other 2 are your train sets. Okay, so you're going to do this 3 times. I'm going to focus on this top left one. So we're going to look at 1 outer session, one of the 3 outer sessions. Okay, so what you do then is you take this test set and you hold it out, and you take the train set and you go into the inner loop with the train set. And the train set is now going to also be split. In this case, we're going to split it into 3. You can choose whatever numbers you want, but we're going to split it into 3. In this inner loop, you split it into 3, and then you do 3 inner sessions. And each of these folds is going to be the validation set once. And that's the validation set. And the validation set is meant to compare models or hyperparameters, different models. And so let's imagine you have algorithms A through Z, or Z, if you prefer, and you want to compare those algorithms. Well, what you do is you train all of them, A through Z, using this train set. And then you measure the validation error. And then you go to the next session. You train all A through Z again, and you measure the validation error. And you do this 3 times because we have 3 folds on the inner loop. And then what you end up with is you have your A through Z algorithms, and each of them are going to have 3 measurements of their performance. And you take the average. And whichever algorithm does best, that is what we call, I'm calling here algorithm selector, your selected algorithm. This is the best one. And you throw out all the rest and you pick that best set of hyperparameters. And this one goes on, and you go back to what you originally had with your test set. You train that algorithm, so that set of hyperparameters, you train it on all the train set, all the training data for that outer session, and then test it in that test set that you held out. And that's the goal. So you get one number from one algorithm on this outer fold. You're going to repeat this process for outer session 2 and outer session 3. And it's important to recognize that the alg select here, the one that wins in the inner loop, may be different for each 3 of these. It could be a totally different algorithm. And that's okay, because it's your pipeline. It's not the model that matters, it's the pipeline.
Yeah, I remember this was the greatest source of backs and forths in our discussions. And again, it's that approach that is the pipeline that we're ultimately validating. And again, so algorithm Z or Z might be the best one in the first inner loop, but in the other ones, it might be another one. But we are finally arriving at performances for the best ones, or the ones we have derived using whatever pipeline that we have. So we arrive at a final performance.
Which is the
which one are we? Which one or how? And I think by now our listeners should know the answer. What are we going to be sharing with others? What model are we going to be sharing with others?
So this is where it actually gets a little more tricky, because we don't just train on, well, you can just train all the data, but there's another step first. So the one thing I want to point out is that your final performance estimate comes from the average of these folds. And again, there could be different algorithms. That's fine. Now, when you're going to pick which algorithm does best or what algorithm you should deploy, you have to go through, you have to repeat your pipeline.
Yes.
Because this pipeline is what you did to estimate the error. So you repeat your pipeline to pick the final algorithm. And so what you do is you take all your data, you do a threefold inner loop. We call it the inner loop. It's just replicating what's happening with this inner loop. You pick the best algorithm from that inner loop, and then that algorithm gets trained using all the data. So you really are just repeating the pipeline that you did to measure the generalization error. And then you use that to pick your final algorithm and train it on all the data.
So you're repeating that inner loop, which is basically your pipeline, but you're applying it to the whole data set.
To the whole data. Exactly.
And that's gonna be your final algorithm that you'll be sharing. But the previous steps allow you to get a sense of the performance of this pipeline, this way of deriving your final algorithm, right?
That's exactly it. That's right.
Yeah.
Yeah. It's a lot to wrap your brain around. But
so what you report is what's at the bottom left, but what you share is what's on the right.
See, that's it. Yep. And you hope that the left part is going to approximate what you get on the right. Yeah. So that's nested cross-validation. Again, it's a beast, but it can be valuable. I think I'm going to leave one out, cross-validation. I'll just simply say it's like k-fold cross-validation, but where your k is equal to n. It's not, I would say it's not very useful in the modern era of big models because it's too computationally demanding. The one that my preference to use is random sampling cross-validation. Random sampling cross-validation has lots of names. It's unfortunate because it's named many different things. Monte Carlo cross-validation, shuffle and split, random permutations cross-validation, repeated holdout cross-validation. All of those mean the same thing, and that's just random sampling.
Yeah.
And it's just like it sounds. What you do is you take your whole data set, you randomly, just using random number generators, pick which data is going to be your train, validation, and test. And then you run through cross-validation, and then you iterate on the next one. And so you pick a new set, and you pick a new set, and there can be overlap, right? You can have the same test data or same data sample in multiple test sets. And that's okay. It's really about trying to approximate, the generalization error. And this is I think, a viable and probably simple approach. I think it's actually very simple to implement. And so it achieves a lot of what you get with nested cross-validation. I don't think we have a good sense if it's more or less biased than nested cross-validation. But due to its simplicity, that's kind of what our lab is using a lot of now.
Right. Yeah. So Tyler, in the nested method, of course, you're trying to cover all the data and make sure things are non-overlapping, etc. Here, of course, things are overlapping. So in a sense, this one doesn't have to be as massively comprehensive in the way it's doing things, but obviously the number of iterations or number of times you do this random technique should be sufficient. Otherwise, you could run into the same problems we were talking about at the beginning, right? If you just do this twice or 3 times, it's not good enough, right?
It's absolutely true. Yeah, and I don't have a number for how many iterations you need. I would love to see more studies of how many iterations you need to converge, but I generally see 5 to 10 in that range is what people use. Is that the best? I don't know. I don't actually know.
Right. In nested we have a sense, right? Okay, this is happening with a 5, 4, 5, 4, whatever, right? But here, okay.
Nested has like a finish line, right? You know what you have to do, and you get to that, and then it's done, right? This kind of iterative method, you could just keep going, right? There's no rule on when to stop.
But in principle, there's similarities in the sense that, okay, here you have a validation and you have the test. So you could be running multiple algorithms, selecting the best one in each of these iterations, in each of these runs, doing the testing, reporting performance, and just do this many times. And ultimately, you arrive at an estimate of the performance of your pipeline. And then finally, of course, you do this training on the whole thing using the same framework pipeline, and you share that model, right?
Oh, yeah, right.
Got it.
That's it.
Yeah.
All right. So that's random sampling. And I think that's the last one I'm going to cover.
Yeah.
So here, this is a table from the paper. And so we went through a lot of them, and it's kind of hard to wrap your head around all of the different cases and scenarios. So we hope this table will be useful to people if you're trying to pick a cross-validation method. We have them listed here. We have indicated whether they can be used for hyperparameter tuning, algorithm selection. We also note their computational cost and complexity, and then just some comments on when they should be used. I think overall, you know, you can go many different ways, but if people ask me what I recommend to people, and I'd say these are probably the three I'd recommend, and mostly just two of them. A one-time train validation test split is great if you have big data. I think it's the way to go if you have just a huge data set. Just be careful not to train too many models. Hold out that test set, don't touch it. And then random sampling is the other one that I just kind of default to. I think K-fold with a folded test set is viable if you don't need to tune parameters, but I feel like in this modern era, I feel like everybody's tuning hyperparameters, so it's not, I don't know how useful it is anymore.
I would say I'm more biased to using the nested, and we use that a lot, and we talked about it extensively. So I think that's definitely one that I certainly.
If you know, if your trainees can understand it and you can get a good pipeline going with it, and more important, if your model's small enough to do it, because again, it can become very computationally expensive. You can't, you know, if your model takes 5 days to train, you're not going to do nested cross validation. Yeah. So, but yeah, I agree. If you can do it, I think nested is great. Yep, it's the gold standard.
Awesome.
So that's kind of the summary of this work. We encourage you to go read the paper because there's more information, but really, I think we went over a majority of it. And I'll just reiterate the fact that I find it interesting. When I was looking up a lot of this cross-validation information, I found a lot of the most useful information came from people in industry, because the people in industry actually cared about over-optimism. Academics tend to exploit it because they can publish that their models are better than some reference standard. But people in industry who actually have to be held accountable to the accuracy of their models, they really are concerned about this issue. And so, so I think we should be in that mindset as well, is that we need to be concerned about
I think in publications by us academics, you know, in this situation, sometimes the demons come out and they're like, yeah, you know, just the results are better if you do it the non-systematic way, as opposed to doing it the right way. And of course, but ultimately, you know, we're hoping that what we do has an impact, for example, in healthcare. So we have to be more systematic. Yeah.
Right. And I think we can get to that. I think just having an understanding of these issues will help.
Yeah. Yeah.
So other summaries point is just, you know, use cross-validation so you don't tune to your test set. And then we have a GitHub page that has examples using MNIST dataset, that kind of the numerical images dataset, and we go through all the cross-validation algorithms. We have code for them that you can implement and run and incorporate into your own pipeline. And then again, encourage you to read the paper. So
yeah. So Tyler, this has been amazing. Thank you very much. And even having this conversation with you, even certain more things just came out, even though I've had multiple with you and as we were going through this, but even this conversation has brought out more interesting stuff in my own mind. So I hope many people can benefit from this work. And so thank you very much for doing this and for being with us.
Yeah, thank you, Armand. You've really you've stretched my mind. You've asked really hard questions over the years that I've had to find answers to. So I appreciate all your help, and I'm as happy to do this.
Thanks a lot, Tyler.